nanomaterials. We heard the introduction. Nanomaterials surround us. We actually use nanomaterials and nanotechnology every single day. Sports good, microelectronics, automotive fields, biomedical devices, it's all nanomaterials. We have it and we touch it every day. Today, I'm going to talk about one particular nanomaterial which was introduced to you a second ago and comes from the oldest, cheapest material you can possibly think, graphite. And the name of this nanomaterial that we can derive from graphite, it's graphene. It's one atom thick layer of carbon. So what you actually can do is, if you think about graphite being made of billions and billions and billions of layers of carbon, then you take one only layer out of that, and then you get graphene. So it's very flexible, as you can think. It's very versatile. The nice thing about graphene is its properties. It's the lightest, optical transparent. It's the strongest material known to man, 300 times stronger than steel. It's a wonder material. The only problem is that it's difficult to make. Now, the discovery of graphene was actually, we need to go back a few years. Two colleagues from Manchester won the Nobel Prize for discovering graphene. And they discovered it by taking a piece of graphite, what you have in your pencil's lead, and took Scotch tape, and they took layer after layer until they found one atom thick graphene. As you can imagine, this method is not very scalable. Industry might have to struggle with that. What we found out under this ERC program was the way of producing billions and billions and billions of graphene sheets in liquid in half an hour. And we use magic solvents, how I call it. So if you manage to choose the right solvents, then they will exfoliate graphite very, very well. And now we came to the next level. We upscaled the production of graphene, and we can produce 1 kilogram of graphene per hour. This is a huge amount of graphene if you think that is the lightest materials known to man as well. So we are taking it to the next level. But we didn't stop there. In about 2010, I actually thought, well, actually graphite is not the only layered material in nature. There are tens and tens of other classes of materials, and within each class we have tens of materials. So it's a zoo of layered materials that we can explore and we can use. Each one of these materials will have different properties because it will be made by different atoms. And now we can start playing material science with one atom thick materials. And we can pick and choose, we can play Legos, we can put one on top of the other, and we can change the overall properties of the devices we make. So we adapt the properties to the final application we have in mind. We can use them in the automotive field, we can use them for energy storage, we can use them in biomedical systems, we can use them in microelectronics as well. So suddenly, playing Legos with the flatlands would open new horizons. And I'll show you now a couple of projects we have in our pocket, really, what we play with every day. We use this flatland of nanomaterials to actually produce printable electronics, printable and flexible screens that would be your screens in the future. You can wrap them up and put them in your pocket. We use them to produce more efficient and more durable, flexible, ultra-thin batteries that will be able to last charge and discharge cycles up to 10,000 times. We can use them for several applications, both in the battery side and in the supercapacitor side. We can use them to make transistors, and microelectronics has the need of shrinking down. We want things which are lighter, more portable, and so we can make transistors made of stacks of layered materials. Conducting, semiconducting, insulating, so we can play literally Lego with these flatlands and obtain faster computers. Another application which is quite fun, but we are exploring, is using these flatlands as gas barrier, and that will allow us possibly to sell beer in plastic bottles, avoiding the short shelf life that the beer in plastic bottles has. Last but not least, we can use these flatlands as thermoelectric devices. So we could engage, we can store the heat that is wasted by engines or your computers and produce electricity out of that in a very, very efficient way. So with this, I finished. I hope I showed you the wonderland of flatlands. And my question to you is over there, where is the future of the flatland? What do you think?
So this is the Ideas Lab, and usually the best ideas come up when you think outside the box. And this is especially true for some old topics, when people always think in a certain way. They don't question anymore the theories or the practices or what they are doing. My example is related to solar cells. And of course, this is the goal that we all want to have, the green Earth. In order to reach this, we just have to make the solar panels more affordable. The good news is that the industry already knows how to make good and rather cost-effective panels. People are actually quite happy when they measure the power output of their brand new solar cells coming right after their manufacturing lines. The problems appear when they put these solar panels outside. They are, after all, solar cells. They must be put outside. The sunlight is harmful for them. Basically what happens, the power output starts to gradually degrade from the initial value. And this degradation can be actually as high as minus 30% from the initial value. And this is actually a big loss. And this will also have a huge impact on the cost of the solar panels. If you think about a standard size of the photovoltaic company today who produces about 1 gigawatt solar panels per year, for them it means millions of euros of losses each year. And now if we think globally, how many companies we already have and how much production we already have, the numbers get much bigger. The problem is not a new one. It's been there for a long time, basically from the beginning. But the impact has become bigger and bigger each year because the technology advances and the solar cell efficiencies become initially higher and we get much bigger outputs initially. But what's causing all this trouble then? Well, you can call it a mystery, but there is one old theory which most people believe in, and that's related to oxygen and a reaction of oxygen with light. However, if you believe in this theory, basically you have to make some trade-offs. You have to use material that is free of oxygen. And this kind of silicon which doesn't contain oxygen is very expensive. So I wouldn't call it as a solution. Therefore, it's a good time to think outside the box. I have background in microelectronics. And previously, I have noticed that in these microelectronic devices, different light sources have caused some troubles for the device operation. And in most cases, the root cause for this failure was found to be ionized copper. Now, having this in mind, I raised the question if the solar degradation that we observe in the panels today is due to the ionized copper. What is even more important and what I'm excited about is the solution that I'm proposing, how we could get rid of this problem. Well, we know that copper is positively charged and it moves very easily in silicon, even at room temperature. And then positive and negative charge attract each other. So what if we put some negative charge on the solar cell surfaces? What happens is what you see in the picture. So we can kind of get rid of this harmful copper. And actually our preliminary results are quite promising. So the next question will be, of course, when do we see this idea in production? What is the time scale? Well, the idea that I just presented to you is very fresh, and I have just received ERC grant to do studies on this topic. So we, of course, have to do more testing on this, but I hope it will happen soon. And then my final slide is about the importance of collaboration between industry and academia, even though we are doing fundamental research. And my question to you is, how can we encourage the solar cell industry to implement these novel technologies into their production? Thank you.
Good afternoon. It is a pleasure to be here today and to have this opportunity to outline to you some of the concepts of advanced nanotechnology. The aim is to identify places, points in possibility space, concrete system-level descriptions of functional systems that are well within the bounds of what is possible and well beyond what we can make today. The identification of these physical systems, the engineering analysis constrained by physics, but not constrained by manufacturing, provides a survey of a landscape of technology that stretches beyond the present frontiers that the human race has achieved and off toward the far shores, the limits of physical technology. And this survey of the landscape sometimes points to pathways and attractive destinations. And as we do that, it pushes out and shows some of perhaps the shape of possible futures. So I would like to say a few words about the exploratory engineering methodology, just compare it to standard engineering. In both practical engineering, by which I mean engineering practice, physical fabrication and so on, we'll compare that to exploratory engineering. In one case, you make products, physical products. The result of the other is knowledge of the potential of technology. Components are constraints. In the first case, they must be manufacturable. In the second case, they must be modelable. They must be susceptible to being described with adequate specificity and confidence to realize an engineering analysis. In conventional engineering, it is enough for a phenomenon to be known. Friction has historically been poorly understood, but rather predictable. In tribology, is a very thriving field of nanoscience, studying the nanoscale interactions behind frictions, complex interfaces and irregular surfaces. In exploratory engineering, there's a stricter requirement, which is that the phenomenon be understood, something that can be modeled well. And in one case, the main cost is manufacturing. The other, it's analysis. Efficiency is important in the first. In the other case, simplicity. And one is looking not for competitive, but for extraordinary performance, the points that are a large distance in possibility space. In conventional engineering, the design must be concrete, concretная. And in the exploratory case, parametric designs are more appropriate in many instances. You describe the scaling and the trade-offs and magnitudes of functional slots and show that the functions, the requirements can be fulfilled. And that leads to very conservative design, large design margins to achieve reliability. So those are the differences, but they are both design and analysis enterprises based on scientific knowledge and experience. So, and that is the domain and some of the methodology. So to motivate the concept of atomically precise manufacturing, I think that one can just step back and look at the world of science and technology and nature and see if there's maybe something missing today. We have seen examples in biology of winged flight and optical imaging, and in both of those domains we have artificial systems that parallel their fundamental principles. Different materials, different performance, different in many, many respects, and yet fundamental physical similarities in both their principles and their function. In the molecular world, there are again some very interesting natural systems. In catalysis, guiding the transformation of small molecules into other small molecules, biology uses enzymes. In programmable molecular assembly, taking digital information from the genetic system and using it to guide the assembly of the building blocks of proteins, which of course can be used for making things like bulletproof vests with silk fiber, and weapons like the horn on cattle, which are hard protein objects. Protein is an engineering material, not meat. It's an engineering polymer. So biology shows us these examples, and in the artificial world we have increasingly interesting and complex organometallic catalysts that, in some respects, rival enzymes. But where do we have the programmable molecular assembly? Parallels are possible, they're not yet implemented. And a study of this domain, what can be achieved there, as we'll see, leads to some remarkable conclusions. Supersonic aircraft are not birds. Space telescopes are rather better than eyes. And programmable molecular assembly systems can go far beyond the ribosome found in biology. So that is the motivation for discussing atomically precise manufacturing. Slightly more concretely, we have two analogies: the nanoscale machinery of biology, on the one hand, the macro-scale factory-style organization that we see in industrial systems. And analysis shows that a merger of the two, atomically precise, nanoscale, moving parts, handling small molecules, all of which are attributes of biological systems, can be combined with familiar components, gears, shafts, bearings, motors, transportation by conveyance, controlled motion paths bringing parts together to achieve assembly. And that is a still image from actually a video available online. And it's another step downstream. I'll show you an image that's derived from that in a moment. So I mentioned the importance of modeling, being able to model reliably, and this concept of atomically precise, very mechanical machines, gears, bearings, motors. Here are some examples of bits of video from molecular dynamics simulations. By the way, there's an illusion here. The illusion is that the thermal motion time is comparable to the mechanical motion time. That's false. You know, the effect of a stroboscopic image, where something can move in a complex very rapidly, yet you see it frozen in one position with a flash of light and frozen in another position. What you see here are the equivalent of stroboscopic images. If you were to watch these with full realism, they would be moving smoothly. The vibrations would be invisible because they would be 1,000 times higher frequency. So imagine these moving very smoothly without the jitter, no vibration. It's a better understanding of the actual physics emerges from that. So these are just examples of some very standard mechanical components, things you find in cars and machinery in factories and so on, modeled using standard molecular mechanics, force fields, Newtonian dynamics, standard techniques implemented in many commercially available and open source packages. So these are easy to model, but cannot yet be built. So there are some physical principles associated with the atomic precision. The first is the observation that the thermal vibration amplitudes, which are the main source of error in guiding the motion of objects at the molecular scale, can be limited in amplitude by mechanical stiffness. With the linear system, you get a Gaussian distribution of probability density, and the tail of that distribution can be made to be very low with adequate stiffness and adequate error margins. So that is a basis for having probabilities of error that are very small, like those in digital logic, for similar reasons. There are energy barriers between the correct result and the incorrect result. So just as digital systems can process bits reliably from state to state, it proves possible for, in essence, the same reason, with careful engineering, to take molecular systems and carry them from discrete state to discrete state with high reliability. And to make the transformations occur in a forward direction reliably, energy has to be expended. And so that is the other part, so it's guidance of the trajectory and energy release to drive forward the chemical processes. And I'll say more about the bottom part in a moment. So there are benefits to working with atomic precision technology. The world is made of atoms. It's very valuable to put the atoms in the right organization. Materials made of carbon can be about 100 times the strength to density ratio of steel, and also far better than the material used to build spacecraft today. It's much easier to build spacecraft if you can leave out, you can omit 90% of the structural mass. And it also enables, as is suggested below, not just the aerospace vehicles, but the ability to make very low energy dissipation, nanoscale computational components will enable the construction of air-cooled laptop-scale computers, laptop computers, that have 1 billion CPU cores and are, again, still air-cooled. So the ongoing exponential revolution in computation still has many orders of magnitude to go beyond the limits of planar silicon. Three-dimensional atomically precise structures can take us much further. And then the other side of this is high throughput. It's very nice to say atomic precision leads to good products, but what will they cost? Biology gives us a hint. Biology builds atomically precise structures, at least at the molecular scale, and agricultural products, for example, are inexpensive. Plants use molecular machinery to make very inexpensive per ton products. Looking at this from the point of view of mechanical systems, the fundamental relationship, which I'll show in, I think, a nicer way in a moment, stems from the fact that smaller structures have higher characteristic frequencies. If you have a constant speed of motion in a mechanical system, in meters per second, linear speed, it turns out that the stresses, the acceleration forces and the stresses in the material are independent of size. The characteristic vibrational frequencies, if you tap it, what are the vibrational modes? The ratio of those frequencies to the mechanical motion times is a constant. And a consequence of this is that if linear motion speeds are held constant, the dynamics scales from large objects to small. You can think of the particles as tracing the same shapes in space-time, but with smaller linear dimension and smaller time dimension. The upshot of all that is you shrink the size of the machine by a factor of 1,000,000. The frequency of operation goes up by a factor of 1,000,000. And therefore, the throughput of an assembly machine, if you think about the scaling, the throughput per unit mass increases by a factor of 1,000,000. So here at the foundations of material interaction with the world, making things, putting parts together, is the potential for a factor of 1,000,000 improvement in productivity. So physics is trying to tell us something. There's a very attractive prospect. So here is a diagram that shows the pathway of some molecules through a hypothetical but physically realistic, fundamental way process. On the left you have the settling molecules. They're binding sites that orient them and hold them in place. Transfer from there to a particular kind of reactive tip, which has been modeled with density functional theory in adequate accuracy to have confidence that the positional control of the energies is what it needs to be. Another interaction, likewise well understood, moves to hydrogens, then you have a pair of carbons, and they come around and they're transferred to build a block. So a small molecule comes in, and it's added to something larger to build a larger structure. Now, come back to going forward from there to large scale, but it's I think, useful to look at this slide first. So imagine that you are building something using a machine system. Okay? I've talked about scaling before. Here's something, we just use round numbers, very simple numbers, to show scaling. We imagine a machine with two arms and it's stacking blocks together. Picks up a block, puts it in place. 8 blocks are put together. If the frequency of completion of a block is 1 hertz, and it's 1 meter in size, and we call this step 1. We have one device. We'll say that it produces 1 kilogram per second, and imagine that the power required for this meter scale device is 100 watts. If we take those components to half size, we now have in the same area 4. So this is step 2, linear size 1/2, frequency 2 hertz, 4 devices. The mass throughput is the same. It's a thinner device, and if you look at the numbers, the mass throughput remains 1 kilogram per second. If we assume, as is appropriate, that the energy dissipation depends on the amount of surface area undergoing shear and the speed of that shear, then if you think about the scaling, you'll conclude that you have the same area of sheared interface, therefore the same power dissipation, therefore that step takes another 100 watts. Well, we can take it another step, and another step, and another step, and at step 24, we have a linear size that is 120 nanometers, a frequency that is 8 megahertz. We have 70 trillion devices, and we still have a throughput of 1 kilogram per second and one more 100-watt stage. That's 2.4 kilowatts, and coming in one side are nanoscale components, and out the other end, mass flow goes this way. Come macroscopic parts. Diagrammed here. On the left, low-cost chemical substances, molecular scale processing as shown, convergent assembly, blocks to put together to make larger blocks, outputting large, precise structures with high throughput. And that indicates, if one goes through the analysis, that the potential is for raw materials cost to dominate the cost of the outputs, which means that the laptop computer with the billion processors costs $1 per kilogram. The spacecraft costs something like $1 per kilogram. That's a radical change from the world we're in today. Higher performance of atomic precision, radically lower cost because of high throughput, simple input materials, and the rest. So I've mentioned some of those advantages from strong materials, the ability to make much better vehicles of many sorts, including the prominent example of spacecraft, much better digital devices, and also what I haven't mentioned is that this has clear applications to medicine. Today, atomically precise structures are widely used in medicine. Antibodies are sometimes used for therapy. They're relatively large examples. Drug molecules are small examples. Our bodies consist of molecular machine systems. Intervening in the body in a controlled and effective way is best done with atomically precise devices. And the prospects for selective destruction of pathogens and for selective stimulation of the growth of cells and tissues to regenerate tissues in the human body is enormous. A very complex area of application, but this provides the means to both understand the systems and to intervene. So in this picture, we'll find that there are stepping stones. I'll say more about that in a while. Intermediate steps forward from present capabilities to further capabilities, leading to, through tools, building better tools, to further capabilities, eventually to the APM level of technology, programmable control of trajectories of reactive molecules, bringing them together. And that leads to a very, very wide range of products that greatly extends the frontiers of the possible. So the question is, where are we today? This is a picture of what physics allows what might the stepping stones be? Go into a laboratory today, in various places in the world, what do you find that might be useful? What sorts of next steps, what research programs lead forward in this area? Well, there are three categories of materials and devices that strike me as particularly useful today. One are structures made of DNA, and I'll show some pictures of those in a moment, which it turns out enable the construction of large frameworks. Another is the engineering of smaller structures, but more in some cases more rigid, more controlled, more functional. And the third are specialized structures, and I'll show some examples of those in a moment. And the net conclusion will be that frameworks plus these intermediate, the protein adapter molecules and specialized components together seem to be a toolkit for making complex nanoscale systems, a major advance on the pathway. And I've outlined these ideas at a number of scientific meetings where people are working on the DNA. Structural DNA nanotechnology is the term, if you want to search for it. Structural DNA nanotechnology. Protein engineering, and they say, oh, this looks like a great idea. And some people are beginning to do it. So, specialized structures, functional structures, all of these exist today. Made by chemists, some by material scientists, some by people working across boundaries and would call themselves physicists. And these structures have a wide range of electronic properties, chemical, catalytic, optoelectronic properties. And people get funding for research in these areas, and they say, look, we've made a potential functional device. But devices aren't enough to make systems. You need some way of putting them together. And here are some examples of DNA frameworks and protein molecules which can serve as frameworks and sockets. So a little bit more on the state of the art here. Here's an example of a protein with, in the middle of it, some heme groups, which are a kind of functional molecule. And this was designed some years back by an interesting methodologist. An example of a design from scratch protein molecule. And proteins can also be designed to bind other things simultaneously, so they can serve as sockets. Specialized structure, hold it with a protein, attach the protein to a DNA framework. And this is an online server for protein engineering. This is a protein design software. So already available software for engineering these precise molecular objects, nanoscale molecular objects. I mentioned structural DNA nanotechnology. These are examples from the first paper on the subject out of Caltech. The designs at the top and the atomic force microscope images at the bottom. The scale here of these structures is 100 nanometers. The state of the art has improved a lot, has advanced considerably since 2006. Here's an example of a design that would be a part of this particular example of a star shape. These structures provide hundreds of distinct sites that can serve as attachment points for sockets for specialized structures. So that is the vision. And here's an example of one with bumps attached to it. Someone sat down and designed this DNA structure, the brown plane, the purple, and a pattern of design on the surface. And this one was designed by Mark Sims, who's a business entrepreneur, and by his high school-age daughter who went to visit Caltech, and it shows the company logo of a company that was working on design software for this technology. So if one steps back and looks at the state of the technology today, it's as though we had a big bag of parts. So you have motors from biology and gears, and you have the equivalent of transistors and wires and so on. But what's needed is the equivalent of mechanical chassis and circuit boards and so on to put the pieces together. And this is a technology that is emerging. People in the laboratory agree that this is a major direction to move. It's really on everyone's list of things to do, and there is progress. We find that in the literature, examples of people putting exactly these sorts of components together to make an initial generation of demonstration systems. That level of technology can be used to get control of the positions of parts. Control of the positions of parts can be used to control the structure of products. Better products can be used to build better machines that give better control of the position of parts, that can be used to put parts together to make better materials, to make better machines. And if you think about our own history, once upon a time there were blacksmiths. Blacksmiths hammered iron. They made better tools for the next generation of blacksmiths. And eventually we had the Industrial Revolution. This will happen faster, but it's the same principle. Tools being used to build better tools. So, returning to this area, I've now shown some of the stepping stones, given an idea of the pathway that we are already progressing in atomically precise fabrication, and leading to this kind of explosion past a threshold. Now, why this matters is far more than academic curiosity or even industrial possibilities, is the magnitude of the impact for the world as a whole. If you trace through the consequences of being able to make better materials, better devices, better systems at a radically lower cost, the conclusion is that the cost of photovoltaics in a very robust, easy to install form can be dropped to a very low cost. But the materials needed to make the physical things of the world can be common materials with lower demand. This points to a future of abundant renewable energy and abundant materials to such an extent that it is clear that that technology base, far superior to our industrial technology, can avoid the vast historic collision between the growth of economic development and industrial resource consumption and pollution, and the impact of that with Earth's limits. That collision has been becoming more and more obvious for many years now. Many people who look forward into the 20th century a bit further feel that it looks very not optimistic, cause for great concern. The emergence of this technology provides a way around those problems by fundamentally changing the material basis of global civilization, much as we've seen happen before in previous revolutions. So this is the slide that I closed with in my talk at the plenary session this morning of the opening session of Rus Nanotech. Pointing out that what this leads to isn't just some new technologies in the future, but a different kind of future. A future in which global problems, many of the ones today, can be solved, where new challenges arise, largely challenges associated with rapid change, and a world in which there's a requirement for some fresh thinking about not just about technology directions, but about national interests, personal interests, what is of value, what kinds of competition are important, what kinds of cooperation are important. And as I said in closing the talk this morning, I hope to see in the coming years the strength of Russian science and Russian vision be applied to this global effort. And for this audience, I'd like to go one more slide and say here's some background material. The first is a book that's a thick exercise in applied physics that examines the physical principles of atomically precise manufacturing in considerable quantitative detail. The second I'll skip over. The U.S. National Research Council did an assessment of this and said, yes, should push forward with research. And finally, a while ago, I was a co-leader of a project with some of the U.S. national laboratories and Battelle, which manages research at several of these, to develop a technology roadmap. I outlined the stepping stones to APM. This is a document prepared in a collaboration of some 200 scientists and engineers from national laboratories and academia in the United States to describe such a pathway, the rewards of progress, and some of the prospects ahead. And I should perhaps mention that if you go to that address, edrexler.com roadmap, you will find a downloadable Russian translation of this document. And with that, we have time for questions, and I'll say, спасибо.